last time we looked at, the last few videos we've been looking at the square root of 2 and how it is not a rational number. And we looked a little bit at why and some properties of rational numbers, or what it is that's wrong with the square root of 2, or what's wrong with the rational numbers that they don't contain the square root of 2. So what we're working toward is building a new number set, the real numbers, that will include numbers like this, that will fix this problem. Before we can do that, or in order to start doing that, we have to get abstract. So what we're going to do with this video is look, we're going to define the set that we want abstractly, meaning the axioms that we want to satisfy, and then after that we'll be able to construct the set of real numbers, which will include the square root of 2. Let me switch pens. That's better. Okay, so properties of numbers, real numbers. So the first thing we're going to look at is upper bounds. And this is really everything that we're talking about. This is what's wrong with the rational numbers, because if you remember, we created a set. We put A and B, where A was the set of all x, element of Q, such that x squared was less than 2. And the problem was this barrier right here, which is where x squared equals 2, isn't in the rational numbers. So everything in B was an upper bound of A, but there was no least upper bound here, okay? So that's what we're going to define now more precisely before we move on. So the first thing we have to define is an order on a set. And a lot of this stuff, as is frequently the case, if you remember, we talked about this with groups too. These are things that naturally we already know about, because just from grade school. We learned it in grade school, how to add and subtract, and sets that the set of numbers that sort of, that satisfies that. And what we've done, what mathematicians have done, is abstract what is important to make the set of numbers, so that we can look and see whether that same structure will apply to other sets perhaps. And we looked at that with groups. So now we're moving on. Groups are one, it's a set with one operation. Rings are a set with 2 operations, and then fields are, add a little bit more to that. So we're just gonna look at fields today. I'm not gonna look more right now, at least, at groups, rings, and fields, but rational numbers are a field and real numbers are a field. And so that's where we're going now. So the first thing is, so one of the things that's abstracted is what is an order. And the definition is just that if you have x is an element of S, y is an element of S, say where S is for some set S, then there's an order on the set denoted by the less than sign, right? Such that only one of the following statements is true. If you have x and y, either x is less than y, x equals y, or y is less than x, okay? So again, this is all what we already know, but we're just abstracting it and defining it abstractly so we can define a set that has the properties that we want. So, right, we already know this about regular numbers, that either x is less than y, x equals y, or y is less than x. And then this is the first thing that makes an ordered set. And then the second criteria that must be true is that if x, y, and z are all in S, and if x is less than y and y is less than z, then x is less than z. So what that means is that the set is like it's entirely ordered from one end to the other. If one thing's less than another, you're not going to find some kind of a circle. It's going to go straight from smallest to largest. And then one last thing, again, just to say it, is that if x is less than y, we can also say that y is greater than x. So again, this is all stuff we know, but now we've defined what we mean by this, okay? So that was what an order on a set means. So an ordered set is a set S in which an order has been defined. So for example, rational numbers is an ordered set if we define r minus s to mean that s minus r is greater than 0, or is a positive rational number. So yeah, actually, so I shouldn't say that. I should say is a positive. Okay, so for rational numbers and for every number that we think of, we can think that this is true. If r is less than s, then that means that the bigger one minus the smaller one is positive. Okay, we'll be using that later. Oh, and I should have said before, I wanted to say that I mentioned this last time too, that this sort of quintessential book, the canonical book on real analysis, is called Principles of Mathematical by Walter Rudin. And this is the book that we're going to be following for the next few, up until we define the real numbers. And then we'll move on to something else, but this is sort of the classic text about real numbers. So what I've been doing now, I'm going through the definitions of things the way that he presents them in his book. So the next thing we have to define is what bounded means. So again, this is all stuff that we really talked about already with when we were looking at the rational numbers, but bounded means that if we have the set S again, is an ordered set. And that there's a subset of S. Okay, so we have a subset, some smaller set of the ordered set. Oh wait, sorry, no. Okay, so bounded just means that if there exists say a beta element of S such that x is less than or equal to beta for every x in E, then that means, or we say, that E is bounded from above. Beta is an upper bound of E. Okay, and lower bounds are defined in exactly the opposite way. So if B is bounded from below, that means that for every that the boundary would be less than everything that's in the set, and then it's bounded from below. So if this is greater than, so if there's some number beta, and for every x in E, the beta is less than the x, then it's bounded from below. So the next concept is the least upper bound. And again, we looked at this too when we were looking at the square root of 2. Because we looked a lot at if we have the sets A and B, the whole point, what we were looking at was that if this is x squared equals 2, that even though everything in B is an upper bound of A does not have a least upper bound. No matter what number you pick in B, you can always find one that's smaller, that's a rational number, because the boundary here is not in the rational number. So there is no least upper bound in the rationals, okay? So if we have a set S, ordered set S, and again with E as a subset, and E is bounded from above, then suppose there exists an alpha in S with the following properties. 1, that it's an upper bound. Of E. And 2, that if you have any gamma less than alpha, then gamma is not an upper bound. Then we call that is called the least upper bound of E. So what this means is, so we, same as above, we have an ordered set S, we have a subset of S, and it's bounded from above. So there exists some A. So we have some S in here. So this is E inside S. And so we have an alpha over here that is greater than everything that's in E, right? So E is bounded from above. So that alpha is an upper bound of E. And also, if you have anything less than alpha, say gamma is over here less than alpha, then it's not going to be an element of E. So that E goes right up to alpha. This is what we talked about a lot when we were talking about the rational, about the square root of 2. Then this is the definition of a least upper bound, because it means that it's an upper bound, but anything less than that is not an upper bound, meaning that it has to be that there's going to be something in E that's bigger than the gamma, okay? That means that it's a least upper bound. And we also call this the supremum. That's the Latin word for it. And one other thing to note is that it's clear from this that there's only one least upper bound to every set, because if alpha is the number that this holds true for, there can't be another one, because anything less than it is not going to be an upper bound. And then we write this as alpha equals sup e, okay? And then we define the greatest lower bound the exact same way. So it's the same thing. So in this case, if we had a set over here that was E, and there was a well, that doesn't look very good. So there's a set here, and there's a lower bound here, and any gamma greater than alpha is not going to be a lower bound, meaning it's going to be inside E. Then this is the greatest lower bound. That we call the infimum. And it would be that alpha equals infimum E. So that means that alpha is a lower bound of E and no beta with beta greater than alpha is a lower bound. Okay? Okay, so let's look at some examples of this, just a couple. So first of all, as I've been saying, just to say it again, the sets that we looked at in our previous videos, where we had a over here, b over here, and x squared equals 2 here, then in this case, x is not an element of the rational numbers. So that alpha has no least upper bound in Q, okay? Second thing, which we also talked about actually in our last videos, is that if alpha equals sup E exists, then alpha may or may not be inside E. So we talked about this. This was actually the first example this was one of the examples that I looked at. So if A is the set of R's such that R is less than 0, then the supermum of A is going to be 0. So this is 0, and this is A, so it's R less than 0. Then the supermum of this set is going to be 0. But the important point here is that 0 is not in A, because A consists only of the numbers less than 0, okay? So the supermum still exists in the rational numbers, but the supermum of a set does not have to be in the set. But if we defined it instead as A such that R is less than or equal to 0, here's 0, then here 0 is now in A, but A has the same supermum. The two of them have the same supermum, because here there's nothing bigger than 0. 0 is the smallest upper bound. Here 0 is the smallest upper bound, but in this case 0 is in the set A. Here 0 is not in the set A. That doesn't matter. They have the same supermum. One more example. This is a good example. So if E is all the numbers (1 over n), where n equals 1, 2, 3. So what is this set? We have 0 here, 1 here. So 1 over 1 is here. 1 over 2 would be here. 1 over 3, 1 over 4, and so on, going over that way, right? Then the supremum of E, so what's the least upper bound of E? It's 1, right? Because 2 is an upper bound, but it's not the least upper bound because anything over here is also an upper bound. 1 is an upper bound, but nothing smaller than 1 is an upper bound because then, because 1 is also in the set. So the supremum of E is 1, but notice that here, the supremum of E is in the set because 1 over 1 is in the set. What's the infimum? So what's the smallest, the greatest lower bound of this set? So these numbers keep approaching and approaching and approaching 0, right? They never get to 0. So 0 is definitely a lower bound. And it's actually the greatest lower bound. Because if you get even the tiniest bit past 0, then you'll be able to find a fraction here of this form that's closer to 0 than that, right? We did this a lot in the last videos. If I give you 1 over 1,000, then you can just say 1 over 10,000. So 0 is definitely the greatest lower bound. But notice that in this case, 0 is not in the set. So the supremum here is in the set. The infimum is not in the set. Okay. Next property. Here's what we've been building up to. The least upper bound. What letters are those? Upper bound property. So remember, the whole point of the last little series of videos was that we could define a set in the rational numbers that did not have a least upper bound in the rational numbers. So there were gaps in the rational numbers. The whole point of the real numbers is we want to get rid of that gap. We want to fill in those gaps. And this is the property that will allow that to be true. That problem of the rational numbers is the thing that separates the rational numbers from the real numbers, is that with the rational numbers, it's possible to define a set that doesn't have a least upper bound. With the real numbers, it's not possible to have a set that doesn't have a least upper bound. That's what this property is. So what this property says is an ordered set is said to have the least property if the following is true. If we have our usual subset, E is a subset of S, and E is not empty, and E is bounded above, then sup E exists in S. So again, as we were talking about, the rational numbers do not have this property because we can define a set that does not have a least upper bound. You can always find a smaller upper bound in the rational numbers. This is an amazing statement because it's so simple and it seems so obvious and trivial that it's like, well, okay, big deal. So for any set, for any set that's bounded above, it has a least upper bound. Okay, what's the big deal? But this is everything because the rational numbers don't have this, and that's what we want to be able to do. We want to be able to always define the least upper bound of a set using a number that's in the set. And again, it seems so trivial and so small an issue. What is the problem? But this leads to, remember how simple the problem was. We just had the following polynomial. This was all polynomials, just, an integer for the exponent, an integer for the coefficient. And this doesn't have a solution in rational numbers. So one way to always think about the ways that math has been extended is that it's all about polynomials and trying to solve polynomials. Remember, what are we doing here? We're talking about the Pythagorean theorem. Even this doesn't have a solution for some values in the rational numbers. That's what Pythagoras hated so much. And then if you just increase the exponent, oops, there aren't any solutions at all for this. That's frustrating and weird and complicated and annoying. And it turns out the problem can be boiled down to this, that there are bounded sets in the rational numbers that don't have a least upper bound in the rational numbers. So we've got to add numbers to that set in order to make it so that that every set has a least upper bound. That's what the real numbers are, and that's what we're going to construct when we're done with these videos.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.